Welcome everybody to the Fast Code seminar. Today's talk is one in a monthly series of virtual talks on the latest topics in the theory, practice, and teaching of software performance engineering. My name is Bruce Hoppy. I co-chair the organizing committee for the Fast Code seminar, and I lead community outreach for the larger Fast Code project, of which this seminar is a part. Before Yihan introduces our speaker, I'd like to take a minute to tell you about the larger Fast Code ecosystem. I'm going to share my screen. And I'll put a link into the chat. So we're looking at the Fast Code website. And this is the landing page for the Fast Code community. And features things like software performance engineering, how to do it, how to teach it, how to help other people learn it, get involved with the community, and events like the seminar. You can see today's seminar on the schedule here, above previous seminars which are listed. We have an upcoming seminar for January, February. It's not officially scheduled, but someone from Google has signed up to tell us about software performance engineering and some tools there. So we're really looking forward to someone from Google speaking in January or February. That'll be announced. And if you have ideas of someone from academia, industry, national lab, anywhere who wants to talk about software performance engineering, please let us know. Me and the organizing committee are listed here, includes Kuba Lackey, Roberto Palmieri, Christian Schultz, Julian Chun, and our host today, Yihan Sun. I want to mention another special event that's part of the Fast Code calendar. We have a workshop coming up at the end of January, part of PPOP in Sydney, Australia, a special workshop on the coevolution of algorithms, compilers, and hardware for performance. So if you're headed to PPOP or any of the affiliated conferences happening simultaneously, we really hope that you'll join that workshop there. There's lots of other things happening as part of Fast Code. I encourage you to check out the website, but I'll keep this introduction brief to give time for our speaker. But first, I'm going to turn it over to Yihan to introduce Chen.
Hey, hello everyone. Welcome to join the talk. So we're very happy to invite Chen Ding. He's a full professor and the chair of computer science department at University of Rochester. He had done a lot of very interesting work on compiler, memory hierarchy, and so on, and especially the part he will mention today about the theoretical foundation for fast code. Very interesting topic. And his work has received the Young Investigator Award from U.S. Department of Energy and Career Award from NSF. He held visiting positions at Microsoft Research and MIT, and he is currently a member of organizing committee of MEMSIS and ICS. He had a lot of very interesting work on these topics. So today he will talk about locality theory 101, the foundation of fast code. So let's welcome the speaker.
Wrong window. Let me try this again.
Looks good.
Right. Thanks, Bruce. Thanks, Yihan. I would say I saw the FastCode seminar last time was actually in person. Regret I can't be there. As Yihan mentioned, I was visiting Professor at MIT at the Cecil Building. I remember visiting Simon, Charles, and Martin in 2007. This is on the slide. It's the CS building at University of Rochester. You probably see it's very different from Cecil. A lot of right angles. To get into the topic, as programmers, we all know that our computers are really memory machines. This is a slide I found online by Chris Terman, showing really the textbook view of the 7-level memory hierarchy, the access time, capacity, and the hardware software system that manage it. So followed by the conclusion that everything is a cache for something else. Indeed, program speed depends on the speed its data access. The modern computer memory is hierarchical, dynamically managed, and often shared. In people, when they think of memory, they think DRAM. It's reliable, it's error protected by ECC. But I tell people, if you think about the cache, it's actually the computer memory that forgets. So this is dynamic, it's complex. It's the reason that although we teach memory is not flat, it's not uniform, when we teach programming, we're actually to large part ignorant of the memory hierarchy. So I would say this is the inconvenient truth of programming. One exception is cache oblivious algorithms and Silk. You must know if you're at MIT. So I taught Silk in computer organization here in Rochester too. So it's in a course that's required for all our Bachelor of Science graduates. And thanks to the help of TB, it was terrific learning material. But the brilliance and the effectiveness of the work is actually they solve the cache programming problem by not solving the problem in that they don't target specific caches, hence the name cache obliviousness. So the goal of locality theory, the topic today, is for programmers to be able to analyze and optimize the memory hierarchy. So it's complementary to algorithm design and Silk. So locality measures, which I'll talk about, can be used to quantify the effect of cache obliviousness algorithms and Silk programs. So, as a picture of computing today, this is the Frontier supercomputer at Oak Ridge. I left this photo of a page in last month's issue of Science magazine. The article is actually about Department of Energy folding 6 scientific advisory committees into a single one. So the photo there is one of apprehension, not celebration. But as an example of new replacing the old, I'm glad we have this community, the fast code community that started and where we can really coordinate our interests and efforts by having this seminar and all the resources that Bruce shows. I really thank Yihan and Bruce for these, for the talk series, and also earlier for the DAX2 seminar in the summer. So let me start by saying the cost of computing is largely data movement. So before Bill Daly moved from MIT to then little-known company called NVIDIA, I remember attending a talk by him at MIT. So this is a slide from his keynote at supercomputing. The green box in the upper left is computing. So it's 64-bit double precision floating point operation. It costs 20 picojoule in energy. And then if you look at the little vertical bar to the right of the box, so it takes 30%, right? 26 picojoule, so 30% more energy to move 256-bit data just a short distance. And then if we access, say, 8 kilobyte SRAM cache, it costs 50 picojoule, 2.5 times of the compute. And if we want to move the data from the edge to the center, that's 256 picojoule. If I want to move the data from upper left to the lower right, it takes 1,000 picojoule, 1 nanojoule. So despite all of this, what's really expensive, dramatically so, is off-chip data movement. So going off-chip by efficient link is 500 picojoule. If we go to DRAM, it's 16 nanojoule. And this again goes, I want to say again, this inconvenient truth is that as programmers, we program what happens in the green box, but we don't program the actions along all these blue lines or the blue boxes. And this slide is from 2010. It's on 28 nanometer technology. What about today? So back in October, I co-organized the International Symposium on Memory Systems. This is an annual conference every year in DC. We invited John Shelf, the head of computer science at Lawrence Berkeley Lab, to give the keynote on co-design for energy efficient computing. The key is actually energy. And then the other keyword is adaptable memory systems, because the data movement really represents the most challenging problem. So these are two diagrams that showing the trend lines from the John Shelf's talk. On the lower left, you see that as we move from 90 nanometers to 7 nanometers, as compute energy decreases relatively rapidly, on-chip interconnect energy, this is on-chip data movement, becomes a lot more expensive relative to compute energy. It's really the point that you saw in the previous slide. And then the power consumption showing on the plot on the right, you see the green dots are the total power per package. So their increasing portion of those are on-chip data movement. But more problematic is the orange dots showing the power of off-chip I/O, which increases much faster. So as we develop faster computers, data movement is going to be the biggest obstacle. Not only is the significant portion of the cost now, but it's also the cost that increases the fastest. So the best solution we have is actually locality. That's the best way of cost control. If the highest cost is data movement, what we want is to minimize that, to have closest access and shortest data movement. So in hardware, the meaning of the locality is really clear. That my work and this talk is about is the question, what is locality in software? And let me say why I care about this, my interest in this. I see locality research as a scientific inquiry, and my skills as those of a programmer and a scientist. So I really like this quote by Noble and Biddle. So to me, the ultimate goal of my work is the program, and performance is what makes computer science a hard science. So the work for me in this is the science of programming. So how to write great programs as a scientific problem. So let me show a little bit what programs we're writing today. So if you program for AI or machine learning, the speaker's last FASCO seminar is certainly doing so. The machine you want is NVIDIA Blackwell Ultra GPU. So this is actually NVIDIA's first chiplet-based architecture using two identical graphic compute dies. Each is about 1,000 square millimeters. And this is the reason I have to go to chiplet, because you cannot build one chip that's twice as big. So having two side by side, each one has 104 billion transistors. So let me highlight the compute capability here. 15 petaflops for FP4. But what we care about here is actually data movement, because that costs energy. And here, data on chip are stored by these L2 caches. You see these 4 purple blocks. Each is about 30 megabytes. So the total is about 120 megabytes of L2 cache shared across all GPU cores. And I have on the good authority from my colleague here, Professor Yanan Guo, actually 2 doors down from where I'm sitting. She's a leading expert in GPU cache side channel attacks. So she told me the replacement policy here is LRU. I mention this because the theory I'll introduce today all assumes LRU cache management. And if we program, so this is our AI GPU servers, if we program, say, your iPhone or desktop devices, this is it'll be a bit dated. It's Apple M1 Max system on chip. Back the highlight. And here's the GPUs. And then you see these big purple boxes. These are the system level caches, 16 megabytes each for a total of 64 megabytes, shared not just among CPUs, but system-wide. Also on this SoC, you have the performance cores. This is 8 performance cores, and not just the system level cache we saw over here, but also each quadrant for performance cores share about 12 megabytes of L2 cache within each quadrant, so a total of 24 megabytes of cache, and that's shared across all 8 performance cores. And then over here, you have 2 efficiency cores, and then they share a cache as well, 4 megabytes. So all of these cases, we have different clusters of processing elements, but what's really important for locality is the cache memory that's dynamically managed and is shared. And similar design is the NVIDIA's DGS Spark that's released just 2 months ago. So if you look under the hood, you see 2 chiplets, one for GPU, one for CPU, and you see the cache shared by GPUs, and then on CPU side, you see performance cores and the efficiency cores, each sharing the cache. So it's a very similar setup. Large caches, asymmetrical, and heterogeneous. And the last hardware slide I'm going to show is the CXL. It's a memory disaggregation. So disaggregated computing is actually a recent fundamental shift in data center and HPC. So I'm borrowing the first 2 diagrams from a MEMSIS paper from Reddy's group. So if you think of a rack scale memory disaggregation, remember the Frontier supercomputers, take the whole rack and then the memory there, connect them through CXL fabric, you get this fabric attached memory. So their locality not only is the between on-chip and off-chip, even off-chip, you could be local or remote. But the access to either local or remote memory depends on the management of the cache, which is dynamic, which is shared, as I've been talking about. All right, so this is what I have about hardware. Let me pause, see if there is any question. Right. If not, let me move on. So far, I talked about the cost of computing is data movement, and the complexity of data movement depends on these hardware designs and the whole hardware now have large amount of cache, dynamically managed and shared. So back to the problem today is how do we define locality in software? We may use the miss ratio, which is precise, it's quantitative, but machine dependent. So I mentioned my goal is a program. Then I want it to run on more than just one machine. Your goal may differ. You may say, I don't care about software or hardware. All I need is to compute the right result and do so quickly. So regardless, we don't write code to run on a single computer. So programs have long lifetimes, machines typically don't. So we need a measure that's machine agnostic, so it's future proof. So in compiler textbooks, we teach temporal and spatial locality. They're machine independent, but they're not quantitative. So they're imprecise. My favorite joke about imprecision is by Moshe Vardi. He stated that you can draw a straight line across any 3 points on a plane if the line is thick enough. So you all know the saying that what cannot be measured cannot be improved. You can't improve what you cannot measure. So as a scientist, I would go further to say that if you cannot measure something, so associate temporal spatial locality with a number, it's unscientific. So in the rest of the talk, I'll introduce 2 quantitative measures of locality that's machine independent. So first is data reuse, and second is working set. And then building on that, we'll go on to the analysis and optimization. So I'll reuse a few slides from a short paper we presented at the MEMSIS with my student Yifan Zhu on 2 properties of data access complexity. So the analogy here is that time complexity measures the processor work, while data access complexity measures the memory work. So locality really means low data access complexity. So my talk today is not about data access complexity, it's really about locality. So next I'll just reuse a slide that covered the basic concept. So we define data reuse as 2 consecutive accesses to the same data item. So in software, a data item is an object. In hardware, which is really a topic today, a data item is a cache block. In virtual memory, it's a page. And then we define 2 measures for data reuse. The reuse interval is the time between these 2 consecutive accesses to the same cache block or same page. The reuse distance is the number of distinct cache blocks, so pages accessed between these 2 accesses. So for example, let's say the sequence ABCCA to 3 cache blocks, and there are 2 reuses, one for A, one for C. The reuse interval and reuse distance for A is 4 and 3 respectively, and for C is just 1 in both cases. And then in the context of a hardware caching, data movement, it means the miscount in demand caching, that is no prefetching. So I will not talk about prefetching here. So I just regard it as an orthogonal issue of data movement. So starting with measure, now we have the beginning of science. My favorite quote from on this defining science is by Randall Nelson, my late colleague at Rochester. He said, science is the art of measurement. So Rochester Computer Science started 50 years ago as largely an AI department. Randall's specialty was robotics and computer vision. Another favorite quote of mine is by John Dewey on this. He said, scientific attitude is both experimental and communicative. So for locality to be a scientific concept, we must define it in a way that we can measure. And next, I'm going to show you two measures. The first one, Reese distance, I already mentioned before. So let me explain this in more detail here. So Reese distance is the amount of data between the use and the reuse. It's the same as the LRU stack distance defined by a group at IBM in 1970. So as a measure of locality, we can associate a number with every axis, and the smaller the number, the better the locality. So next, I'm going to show you example. This is what I call the ABC example of locality. So given the simple repeat of 3 axes to 3, say, data blocks, what is the locality? Now, if we measure by Reese distance, the first 3, because they're first-time accesses, by convention, we say the Reese distance is infinite. For the next 3, the Reese distance is 3, because there are 3 distinct data items access between the use and the reuse. So if I change the order just slightly to repeat second time differently, instead of ABC, I do CBA. The Reese distance for the first 3 is still the same, but for the next 2 is different. For C is 1, for B is 2. Now we have the measure. These are different numbers, therefore they have different locality. And here it's really a good demonstration what this concept is. So you can say data are all created equal, but they're not accessed the same way. That makes a difference in locality. People often think locality as frequency. Something is accessed a lot, it's considered hot. If you know martial arts, you know Bruce Lee, who said, I fear not the man who practiced 10,000 kicks once. I fear the man who practiced 1 kick 10,000 times. So that's the frequency concept. But hot data actually it has greater locality, but by itself, frequency is not a complete measure of locality, which is shown exactly by this example. So in this example, we have 2 sequences, the same data size, the same access count, but different locality. So locality as a collective phenomenon, you cannot actually quantify it by looking at single data block by itself. So quantifying locality is actually quantifying their group effect. It's the sequence in the order in which the data is accessed. So with the Reese distance, with a quantitative measure, we see that not just which sequence has better locality, we also see that exactly where the locality is better, which axes have lower Reese distance. And Rochester is a city with many musicians, and the university also have many students into music. When I teach this here, I'll often ask students if you play instruments, and if you do, when you practice scale, do you repeat by the order of ABC, ABC, or do you repeat by ABC, CBA? And it's in almost all cases, the pupils were taught by practicing ABC, CBA. I remember a student actually explained to me that think of if you're playing clarinet, when you just finish ABC, the next note, you just played C. So you have this good muscle memory to play C again. And there you see a tantalizing connection. Right? What's good for computer memory, the locality we're talking about here, is also good for muscle memory or biological memory. So to repeat, locality is, as shown by the ABC example, is a property of sequencing. So like music, so music is not a collection of notes. It's really how the notes are ordered. That's actually why music includes gaps or air. So it's basically how do you create something from nothing? It's because of ordering. So same with locality. It's not about data, it's about data access. So it's not about nodes, it's about the melody. So that's the Reese distance measure. So next, I'm going to show you the one that's it's more important for the rest of the talk is the second measures. So again, you must have heard program as working set. And again, let me take analogy with people. Think of a person with short attention span. So think of our programs as people who live in the moment. The original working set theory was actually part of the seminal work of the working set model developed by Peter Denning, who was an undergrad at MIT working with Jerry Salter and Jack Dennis. The theory by Denning is stochastic. It analyzes generative processes, but it has this brilliant result that the average working set size can be computed iteratively using a recursive equation. So I refer it as the Denning recursion. I made sure that Peter agrees with this name by having him as a co-author of our paper. But it wasn't clear how you define working set size when you have a finite sequence, which is a program execution. So fast forward almost a half century, my then student Xiaoya Xiang led the work that defined footprint in any finite sequence. So the footprint of the function fp x is the average working set size for all windows of length x for x greater than equal to 0. So this parameter x is what we call a time scale. You think about a day is a time scale. It's not about any particular day. It's really a length of time that's 24 hours. Our circadian cycle is a time scale. It's interesting for me when I learned that our internal clock is actually longer than 24 hours, and then it's just synchronized by our daily activities. One of the undergrad at Rochester, Colin, who worked for me as REU in one summer, lived a 25-hour day schedule. It was tricky to schedule our weekly meetings, as you can imagine. Now, let me use the same example and then measure their locality using this metric of footprint. So for ABC, if we set the time scale x to be 3, there's 3 windows of length 3. Each has working set size of 3. So the footprint at x equal to 3 is 3. For ABC-CBA, for the same time scale, we have same 4 windows, but 2 of them now have working set size 2 because of reuses in these 2 windows. And the footprint is smaller, it's 2.5. So at time scale 3, ABC footprint is half unit larger than ABC-CBA. So we have 2 measures of locality. So they both actually agree that ABC-CBA has a better locality, but for different reasons. So next, the natural question will be, is there a relation between the two? So let me get to that connection. That's the relational theory of locality. So in the abstract of the talk, I talk about common problems of poor locality. It can be due to too many cache misses, that's a data movement, lack of data reuse, or too large working sets. So the connection question is, are they three different problems, or are they three manifestations of the same problem? So are these three monsters, or a single monster with three heads as the Cerberus? So relational theory answers that question by converting between locality measures. So here we now take a step from observation to explanation. So it's correlation, if not causation. And the explanation, it's problematic whether we know something true or not. So I read New York Times, there's some of the titles, it's very tantalizing. It says, the rise of social media and the fall of democracy. Is that correlation or causation? But the recent article, humanity fails as AI rises. I hope that's not causation. So the relational theory is really a scientific theory. It's about the relationship between locality measures. So I would say the goal is similar to the physical equations. So the most famous is probably E equal to mc squared. That shows that energy and mass are equivalent, and you can convert it. Here, I'm going to show conversion between locality metrics, hopefully not as explosive. So this is probably the most important slide. It's the conversion by the what we call higher order theory of locality, so HOTL. So this particular one is from footprint, which, as I defined, to miss ratio. So from locality measure to data movement. The miss ratio for cache size C equals to the finite difference of the footprint function at the point when footprint is the cache size. The finite difference is simply at point X is simply fpx plus 1 minus fpx. And if you look at this visual showing the time scale, starting from 0 on the left as a line segment increasing toward the right, we start with time scale 0, 1, and the footprint when the window lines is 0 is 0. When window lines is 1, it's 1. So if I want to compute the miss ratio for when we have no cache, so cache size is 0, we would find the point where the footprint is 0. So that's really the FP0, and take the finite difference. So take FP1 minus FP0. FP1 is 1, so the minus result is 1. So if we don't have a cache, if the cache size is 0, the miss ratio is 100%. So this is a simple sanity check that at the extreme case. If our cache is, say, any size of C, how do I compute the miss ratio for that cache? So same procedure. We find the footprint at a time scale that's equal to C. So fpx equal to C. And then when we think about what's happening here, I have this working set over the last x-axis. The next one to access at time x plus 1 is either a cache hit. In that case, my working set size is the same, or it's a miss, then my working set size would increase by 1. So the miss ratio is the average probability that my working set size increase. So that's the finite difference. It's fpx plus 1 minus fpx. So that is the miss ratio. And from this, we go from a function of the footprint to a function of miss ratio. And this is the part of the relational theory of locality is really about converting between locality metrics. So this diagram visualizes the relationship between definitions of locality. So I should first give the definition of a locality definition. So a locality definition is a equivalence relation among all execution traces. So two executions are equivalent if and only if they have the same locality by that definition. So each locality definition is really a partition of executions into equivalence classes. So a trace itself, think of ABC, is a measure of its locality. So we can call it a singleton locality. The name singleton is adapted from the work by my colleague, Professor Michael Scott, so 3 doors down from my office. He and then his student Li Lu defined determinism as an equivalence relationship among concurrent executions. So the locality definition, as I defined, is actually the equivalent interchangeable terms as locality measurement. So singleton locality requires no measurement. In all other cases, the way to measure locality defines the locality, whether it's reuse distance or footprint. Oops. The footprint is actually here. And this edge shows how we can derive the footprint from reuse interval histograms. You can do so in linear time complexity using a formula invented by Xiaoya Shang, so we call Shang formula here. So in this diagram, each node represents a distinct locality metric, and direct edges between nodes indicate conversion relationships. And the paths form by the direct edges implies transitive conversions. And the metrics are organized into categories. The access locality associate locality measurement with each access. Time scale is the footprint with time scale parameter, and cache locality will be cache misses, as well as other measures. In particular, average eviction time is something that my collaborators in the past at Peking University used productively and found many applications in model software caches. And I also want to talk about the term. So you may hear I say locality metrics. I might say or measures, use them interchangeably. Measures are broad. Any quantifiable data point is a measure. So to be pedantic, not every measure is a metric. A metric must satisfy 4 properties shown on the slide. So all the measures, reuse interval, reuse distance, and working size, are non-negative and symmetrical. But what about the 0 case, second property, and the triangular inequality? So the key here is actually defining a window so that the working set size is a metric that has all 4 properties. And then using the same definition window, I can define reuse interval, reuse distance by the reuse window. And so by doing so, we can see that the reuse distance for AA should be 1, not 0. And so when I say locality metrics, even though it's RIRD, strictly speaking, are not metric, but they're more metric-like than metric dislike. So I mentioned least recent used replacement policy. In the analysis, there's actually subtle difference in cache management. LRU is what you know for hardware cache, most used in the real cache system. But there is another notion called working set cache. So in working set cache, the data is kept for a time length X. The footprint, the Hauto conversion that I showed, is actually computing the miss ratio of the working set cache. So it has been mostly for theoretical analysis, except that we have developed a real cache called the least cache system. The least cache was first studied in 2019 paper in ASPLOS, co-authored with John Criswell, my colleagues next door. But it was made into a real hardware cache by Professor Doran Petru at Rochester Institute of Technology. So we collaborated and published the papers shown here. It started as a working set cache, actually developed during the pandemic years, and now it's programmable cache. So remember what I said about the inconvenient truth that we program computation, but not the cache. With leases, we actually can program the cache. But this is just a digression. It's not the topic today. So locality theory over time has a lot of applications for the reuse distance or LRU stack distance. There are also 4 decades of algorithmic improvements in how to measure the reuse distance in a low asymptotic cost. Footprint is really a breakthrough because you can now compute this using the Shell formula in linear time, and then we can convert footprint to miss ratio. It's really a purely mathematical operation. So one thing that's really new since 2010s in locality theory is that similar to Hauto, the locality analysis and optimization can now entirely done as math operations on functions. It's in particular the footprint function. So footprint locality is defined on all non-negative integers, and footprint is monotone and largely concave. So that's the remaining part of the talk is locality optimization. So the theory is for us to go beyond intuition with cache system, with scale and the complexity. It defines simple intuition. Engineering often rely on rules of thumb. They're often effective, but they're imprecise and brittle. So the example is so-called square root 2 rule of cache scaling. This from database communities, that if you double the data size in the workload, you have to increase the cache size by 40% to maintain the miss ratio. That's a rule of thumb. It shows cache scaling, how cache size should grow proportionally to the data demand. But rules of thumb are imprecise. So remember what I talked about the Moshe-Vardy stroke before. It's also brittle. It doesn't say when it works, when it stops working. So now I'll give you another joke about the fragility. So in the Hemingway novel, a character asks his friend, so how did you go bankrupt? The friend said, first gradually, then suddenly. So this is my second joke about imprecision. Speaking of rule of thumb, this is the recent rendition on the cover of Science magazine in September. So can theory help? Can we do better? So I just have 2 examples to show you. I mentioned cache sharing. In this diagram on the top, if I have 2 processors and 4 programs, I have the choice of which 2 programs to run, share the cache. And there, the number choices is quadratic. So if we have n programs, we want to best pair them up. The full numeration will be n choose 2 co-run tests. With footprint, we can have the compositional analysis. So that means we predict the miss ratio of any pair program runs using metrics measured only once for each program. So instead of exhaustive testing, this composable analysis has a linear cost. So the way to do that is to have stretched footprint. So a program footprint, as we mentioned before, what it is, now it needs to be stretched based on the portion of access in the interleaved execution. So in the formula on the lower left, FP1, FP2 are stretched by their access rate, AR1 and AR2. So essentially, the footprint are based on time scale. So the stretching is to standardize the time. So before stretching, the program has its own time. After stretching, they share the same time. So once synchronized, we compute the combo footprint just by mathematical function addition. Visually, the purple curve here shows the combo effect of footprint. Now, how do I compute the miss ratio, the Hauto conversion? So when I find the cache size, when I find the footprint that's equal to the cache size, so when I have the cache size, I find the footprint at the time scale where I have the footprint equal to cache size, the finite difference gives me the miss ratio of the shared cache. And then for each footprint, I can do the finite difference to find the miss ratio of each co-run program. So it's all just mathematical operation. And then another one, if I have a few more minutes, is even, I would say, more interesting. So first, let me introduce the notion of exclusive cache hierarchy. So if you look at the diagram here, and think of a program as a CPU core. When I have two levels of cache, the inclusive cache, long used by Intel, means that the content of the upper level is replicated at the lower level. So that's inclusive cache. Exclusive cache is actually shown here. So there's no replication. The cache data is either in H or in L. So the L is known as the victim cache because it stores the evicted data from H. And when we have multiple cores, the H will be private and then L will be shared. So this is actually a reason the multi-core direction is the reason that the Intel had to give up on inclusive caching, because as the number core increases, you can't afford to store all the private cache content into the shared cache. So as a result, all modern multi-core GPUs, CPUs have a non-inclusive cache. So the shared cache L is actually shared victim cache. And this is the what's being said here. Now, with exclusive cache, how do we model? So back to the single program case, because H and L are exclusive, so really there is no difference in the single core case whether we have two-level exclusive cache or just single-level cache with combined size. So that is this victim cache requirement. So for a single program using inclusive cache hierarchy, the miss ratio must equal that of combined cache. So how do we compute the miss ratio? We do so with footprint, as was been talking about. And then without going through the derivation, the work led by Chen Ding derived the victim footprint from footprint. So it's really a function translation of footprint. So if the mathematical terminology, this is a function translation. The victim footprint is a function translation, both horizontal translation by X and the vertical translation by H. And then we proved that the victim footprint is the only solution that satisfies the victim cache requirement. So not only we have the unique solution, and then we also, because its footprint is composable. So this is really it's entirely mathematically derived, but worked really well experimentally as well, as we discussed in the paper. But one thing we didn't realize is that we did not pick a good name. So if you search victim footprint, you can't find our paper. So there's example that science and culture intersect. All right, to summarize, I have shown the essence of computer memory. It's hierarchical, dynamically managed, and shared. That's the motivation. And then a theory, you may say, it's a glass slipper that never quite fit the foot of any real system, or it may let us see around the corner before turning. So a theory, it's a model. As the saying goes, all models are wrong, but some are useful. What's really useful here is precision. So I talk about relational theory of locality, the metrics, reuse interval, reuse distance, and footprint, and the conversions, in particular, the Hauto conversion from footprint to miss ratio. And then the theory-based optimization, this one is the composition through function scaling, and the composition that's modeling the shared cache for partition sharing. And then by solving equations mathematically and deriving a translated function to be the victim footprint to model the exclusive cache and sharing. So one thing I hope to talk about in the future is polynomial time data access complexity. So that would be the technical side. If you don't remember the theory, at least I hope you remember the two jokes I had about imprecision.
Thank you, Chen. I'm definitely going to remember the jokes and want to see if anybody has any questions for Chen. You can type them into the chat, or the group is small enough, you could just unmute yourself.
I have a quick question.
Yes.
So, yeah, so this is very interesting, and I'm wondering if there work showing the measurements and the running time, like how they are related, and are there experimental results showing the relationship between them?
So the correlation between, say, miscount and the running time.
Yeah, like yeah, so some experimental study, are they like generally linear or are there other like relationships?
We have So there, we have some limited data on that. The on CPU systems, which is really most of our experiments have been on, because of prefetching, the relationship is not direct.
Mm-hmm.
So that's really a good question. With the workload so far, I would say no, in the sense that when we evaluate the model, we compare with simulated systems there we have control. So there's
Mm-hmm.
it's experimental design, so how you minimize the number of unknowns. So prefetcher is definitely something that's unknown.
Okay.
I
So
have
when
Thank
a
you very much.
follow
Yeah.
yeah, yeah.
follow-up question related to that. Uh, Chen, does your answer relate to your comment just a minute ago about you might see this as a glass slipper that doesn't quite fit, or something that lets us see around corners? Is that kind of referring to your answer to Yihan's question?
Right. That's yeah. Uh, so the type of data we have is the number one, compare with the cache simulation, because there is what we model. So that measurement has to agree. The other one is to use hardware counters on actual machines. That's to address our assumption of the cache replacement policy. Whatever we can simulate may not be the same as in the real hardware. So the hardware counter there would give us a more direct reading. So for the exclusive cache performance modeling, we did have results for the hardware to compare with hardware counters. And I think for performance, when we use this co-run optimization, I think I have to double check. We also may have done performance measurements as well.
Thank you,
Got it.
Chen.
Thank
Any
you.
other questions for Oh, here's one from Libby. Do you want to unmute Libby and ask it?
Sure. So a few slides back, you mentioned software solutions, but then you weren't really going to talk about them. But I'm wondering if some of those software solutions you were talking about are where we're going to go to alleviate the data movement performance problem.
Thanks for the question, Libby. Do you refer to the slide when I talk about the lease cache and cache programming by leases?
Yeah, that was probably it. Yeah.
Right. And then that also connects to the Ihan's question about performance on real systems. So lease cache is a way for software to control how cache is management, as opposed to now the paradigm is hardware managed cache. So replacement policies is actually reactive. Leases is our design to let software to manage the cache directly.
Right. So will that then, in theory, make the issue of the orange line that you mentioned at the beginning come back?
Right. So that's one tool to reduce the data movement. If I manage the cache on chip, then I don't have to move data as much.
Right.
Yeah, you're exactly right.
Thank you.
You're welcome.
Thank you, Libby. And thank you again, Chen, for a great talk. And I'm going to wrap things up. Chen, I assume people can email you if there's additional questions or desire on following up, or you want to say any last words on that?
Oh, certainly. My information, you can find it on University of Rochester website. And thanks everyone who came here. I wish everybody a good end of semester if you're students or faculty, and have a good break.
Thank you, Chen, and have a good break, everybody. We'll be back in the new year. Take care. Bye.